Another method that can be used for integrating expressions, in this case rational expressions, is the method of partial fraction decomposition. Take, for example, a rational expression such as 1 over x squared minus 5x plus 6. If we were to choose to integrate that, we would have a few options in front of us. Most recently, we talked about integration by trigonometric substitution. And while this does not exactly fit that, we did see an example where we can alter the denominator by completing the square. If we could complete the square here, which it is possible to do, then that would allow us to use trigonometric substitution to integrate this expression. However, completing the square is not going to be pretty because the coefficient of the x term is odd. That means that the constant term that needs to be there to complete the square will be a fraction. And that's going to make things rather messy. Not just in the factored form of the completed square, but also then in the constant term that is next to it, which then has to be written as something squared yet again. This is going to get really ugly if we attempt to do it that way. However, partial fraction decomposition gives us another option. The idea is that when we add rational expressions, we take expressions with smaller degree denominators, and in the process of finding a common denominator, we end up introducing new factors to each denominator so that we produce a single fraction with a larger degree denominator than the original fractions we started with. For example, if we were to take 1 over x plus 1 plus 3 over x minus 2, in order to combine these, we would have to multiply the left fraction, the first fraction, by x minus 2, and of course in the numerator as well. And to make them have the same denominator, this would need to be multiplied by x plus 1, top and bottom. And as a result, however the numerator ends up simplifying, the denominator is now going to have an x squared, a degree 2 polynomial in the denominator. Well, if we can combine two fractions with smaller denominators to get a single fraction with a larger degree denominator, then why can't we take a single fraction with a large degree denominator and break it down or decompose it into smaller pieces, smaller parts, hence partial fraction decomposition. The idea is that if we were to finish this addition, we would have x minus 2 from the first numerator plus 3 times x plus 1 from the second numerator over the now common denominator. And this would give us, when all is said and done, in the numerator, 4x plus 1 over, if we chose to expand the denominator, x squared minus x minus 2. So wouldn't it be nice if we had a way to take an expression that started out in this form and take it back to the original two smaller, if you will, rational expressions that were added together to produce this thing? So how exactly do we go about that? Well, this is going to require a really particular bit of algebraic knowledge that is not overly emphasized in an algebra class, but at this point it suddenly becomes a very important corollary. The fundamental theorem of algebra states that any degree n polynomial must have exactly n solutions, counting unique real solutions, repeated real solutions, unique complex solutions, and repeated complex solutions. What that actually all means, another way of thinking about that, is that all polynomials with real number coefficients can be factored into a series of linear and or irreducible, meaning it cannot be factored any further, irreducible quadratic factors. This is a corollary of the fundamental theorem of algebra. If every polynomial degree n has n real number solutions, each real number solution has to come from a linear factor or correspond to a linear factor. For example, if x equals 3 is a solution, then that corresponds to the linear factor x minus 3. This can be done with any real number. Complex numbers then are going to come from quadratic factors that have complex solutions. Other irreducible quadratics may produce real solutions that are, unfortunately, irrational, but they are still real numbers. So every polynomial must be able to factor down to these. And we can use that concept to help determine the nature of partial fraction decomposition. So, for a rational function, which has a polynomial in the numerator and a polynomial in the denominator, specifically where the degree of n of x in the numerator is less than, strictly less than, the degree of the denominator d of x. If this is the case, d of x, being a polynomial, can be factored into linear and irreducible quadratic factors. All linear factors would be of the form px plus q. Now, it is possible that some of those linear factors are repeated, which means that they happen multiple times, and hence the exponent of m. So each linear factor would be in this form. Quadratic factors would be of the form ax squared plus bx plus c raised to, again, a power, because they could, in theory, be repeated. Each factor of the denominator let's start with the linear ones. Each linear factor, would break down into the composition of a constant numerator over the linear factor to the first power plus another constant over the linear factor to the second power plus a third constant over the linear factor to the third power, etc., until we get to the actual power itself, the mth constant over px plus q to the mth power. So if a linear factor only occurs once, we would only have a single fraction. If a linear factor occurs 3 times, we would have a sum of 3 factors, accounting for each power of that factor. Likewise, for each quadratic factor, they will decompose, well, very much the same way, except since these factors are going to be quadratic, their numerators are going to be linear. The idea is that each fraction that it breaks down into, the degree of its numerator should be exactly 1 less than the degree of its denominator. This coincides with the fact that the original fraction should also be of a lower degree than the degree of the denominator. In order to keep with that, we make sure that each of the partial fractions also has a lower degree in the numerator than it does in the denominator. Likewise, if this is repeated, then we can have a new expression in the numerator with different coefficients, and so on, until we reach the nth factor of ax squared plus bx plus c. Now, this is true for when the degree of the numerator is less than the degree of the denominator. What happens if it's not less than? What happens if the degree of the numerator is equal to or greater than the degree of d of x? Well, in that case, we can actually divide them, which is always an option with rational functions, provided the numerator has a degree equal to or greater than that of the denominator. We can rewrite the rational function by actually dividing the numerator by the denominator, which will produce a polynomial quotient plus a polynomial remainder over the original divisor. But in this case, the remainder will always be of a smaller degree than the degree of the denominator. This is called the division algorithm. The idea being that we then change this rational function into a straight up polynomial. That's q of x. It will just be a straight polynomial, which for the purposes of integration is very easy to work with. And then this can be decomposed. Because now this fraction, this remainder fraction, will be of the proper form where the degree of n is less than the degree of big D. This necessitates examples. It's very vague, it's very weird, it necessitates examples. So let's first, before we get into any calculus with this, let's first look at an example where we simply are going to determine the partial fraction decomposition. We will take the rational expression I wrote at the very beginning of this video, 1 over x squared minus 5x plus 6. The first step, as we said before, is to make sure that the numerator has a degree smaller than that of the denominator, which it clearly does in this case. The second step then is to fully factor the denominator into linear and or irreducible quadratic factors. This, fortunately, factors quite simply as x minus 2 times x minus 3. According to the rule of partial fraction decomposition, then, this single rational expression would be equal to the sum of two rational expressions, one with x minus 2 as its denominator and a constant numerator, and the other with x minus 3 as its denominator and a constant numerator. Now, if you choose to use capital A with subscripts for both, that's fine. We did that earlier in the video in describing the decompositions because we were using the unspecified exponent of m or the unspecified exponent of n. So we kind of had to use subscripts because if the powers were big enough, we could, in theory, run out of letters of the alphabet. But here, since we are looking at only two fractions, we only have two variables to deal with in the numerators, it's very easy to just use A and B. So this is what we're looking at now. That the fraction 1 over x minus 2 times x minus 3 is equal to some numerator over x minus 2 plus some other numerator over x minus 3. The way we proceed from here to solve for the values of a and b is to first clear the denominators by multiplying both sides by the common denominator, which of course will completely wipe out the denominator on the left side. On the right side, we will see some cross-simplification. When the x minus 2 times x minus 3 multiplies the first fraction, the x minus 2's will cancel and leave us with the a times x minus 3. When the common denominator multiplies the second fraction, it's the x minus 3 factors that will cancel, leaving us with the b times the x minus 2. And as we already noticed on the left side, we will be left simply with 1. Now we could do some algebra here to distribute the a and distribute the b and combine some like terms, but it's much faster and easier here to solve for each of the variables a and b in turn by selecting an x value that will eliminate the other variable. So we can eliminate a by using x equals 3. Because substituting 3 here will produce a 0 that multiplying the a will cause it to cancel out. Thus, we're left with 1 is equal to b. Likewise, we can eliminate the b by letting x equal 2. Eventually leaving us with a is equal to -1. Thus, our rational expression 1 over x squared minus 5x plus 6 can be written as -1 over x minus 2 plus +1 over x minus 3. The idea being now that we have an equivalent form which, in some cases, may serve us better, specifically with regard to integration. So, for example, if instead of simplifying the partial fraction decomposition, if we instead were looking to integrate this rational expression, we could instead integrate its alternative form, which is certainly preferable. Again, is it possible to integrate this rational expression by other methods? Yes, but it will get very ugly to do so. On the other hand, each of these fractions should integrate quite easily. They both have a degree 1 denominator, a linear denominator, which means that they will fall nicely into a natural logarithm. If you wish to go through the substitution process, you certainly can, but ultimately, the numerator will become a coefficient, and then we will have the natural logarithm of the absolute value of the denominator. And then the same thing for the second fraction. And of course, our plus c to round it out. Again, feel free to go through the steps of the substitution for each of those if you feel it is necessary, but since both denominators are linear and both have a lead coefficient of 1, you should find very quickly that this integration is quick and easy to do. Let's look at some other examples now. Some things that perhaps get a little bit more, give us some more variety in our functions. Excuse me. Example 3. Suppose now we have the integral of the rational function 5x squared plus 20x plus 6 over x cubed plus 2x squared plus x dx. Now we are in the proper form for partial fraction decomposition since the numerator is degree 2 and the denominator is degree 3. So we can proceed to factoring the denominator. First by factoring out a common x. and then by factoring the remaining quadratic into the repeated factor x plus 1 squared. Thus, we'll come back to the integration later. Thus, the rational expression 5x squared plus 20x plus 6 over, at this point I will write its factored denominator, over x times x plus 1 squared, would have a partial fraction decomposition equal to the sum of 3 fractions. A constant numerator over the linear factor x. And then since x plus 1 is a repeated linear factor, we're going to have a constant numerator over x plus 1 to the first power, plus a different constant numerator over x plus 1 to the second power. So a little bit bigger than the previous example. Will take a little bit more work, but again, at this point, we should be used to the idea that none of these problems are tiny. Most of them are going to require a significant amount of space to work through. So, like on the previous example, we're going to have to multiply both sides by the least common denominator, which, on the left side, will always completely wipe out the denominator that's there. Again, remember, this side being the sum of the 3 fractions on the right already contains the LCD. When we multiply each fraction on the right by the LCD, only the factor that appears in the denominator already will cancel out, leaving us with the other remaining factors to be multiplied by the numerator. So when we multiply the LCD times a over x, the x factor will cancel out, and we will be left with the x plus 1 squared. Likewise, when we multiply b over x plus 1, this time the x factor does not cancel out, but one of the factors of x plus 1 does. So we will still have the x factor and one factor of x plus 1. When we multiply the third fraction, both of the x plus 1 factors will cancel out, but we will be left with the x factor. Now again, we can expand the right side and combine like terms. That is an option. But we can always find at least some of the values a, b, and c with some careful substitutions. Most obvious here would be that we can eliminate the c by letting x equal 0. Which, since the b times x plus 1 also has a factor of x, will actually also eliminate the b term at the same time. So we will start out by letting x equal 0, which, on the left side, will result in just 6. And on the right side, will result in the c term and the b term both simplifying out, thus leaving us with just the a times 1 squared, which is simply 1. Thus, a is equal to 6, and we have our first numerator. We can eliminate the a variable very easily as well by using x equals negative 1. Negative 1 will cause the x plus 1 squared factors to both be 0. And likewise, since the b term also has a factor of x plus 1, choosing x equals negative 1 will also cancel out the b term. So again, we will have on the left side negative 1 substituted for x, which, working through the arithmetic there, will leave us with negative 9. On the right side, negative 1 plus 1 is 0, which will, when multiplying by the a, will cause that to drop out. And again, negative 1 plus 1 is 0 here. So ultimately, on the right side, we are left simply with negative c. Dividing both sides by negative 1 tells us that c is equal to 9. And we have our second numerator. Now, unfortunately, there is no way to get the a and c to both eliminate, thus leaving us with b. The a term in this and the c term do not share any common factors, so there is no single value of x that will get them both to cancel out. However, we now know the value of a and the value of c. Using those values along with any other value for x will leave us with simply the b as our only variable and thus allow us to solve for it. So I'm now going to choose, well, really, the simplest x value that there is, besides the 0 that we already used. We're going to use x equals 1 along with the knowledge we already obtained that a is equal to 6 and c is equal to 9. So again, on the left side, we have 5 times 1 squared times plus 20 times 1 plus 6. On the right side, we have 6 for a, and now we have 1 for x, plus b, which we still don't know, times 1 for x, plus c, which is 9, times x. Cleaning up the left side, we're going to end up with 31. 1 plus 1 is 2. 2 squared is 4. Times 6 will give us 24. The second term simplifies to 2b, and the last term, of course, is just 9. Subtracting both the 24 and the 9 from the left side leaves us with negative 2. Dividing both sides by 2 tells us then that b is equal to negative 1. And this is our third and final numerator. Now we are ready to rewrite our integral using our partial fraction decomposition and thus integrate it. So our original expression was 5x squared plus 20x plus 6 over x cubed plus 2x squared plus x dx. And this can now be rewritten as the sum of the three rational expressions, 6 over x, plus negative 1 over x plus 1, plus 9 over x plus 1 squared dx. As with the previous integral that we did, the fractions that have a linear denominator with a coefficient of 1 integrate very cleanly. However, in this case, we have that repeated linear factor in the third fraction. That one may be a little bit less obvious. So again, going through the integration by substitution, is not a bad idea here. I'm going to omit it from this video, but you should be in the practice of doing it yourself. This will result in the numerator 6 times the natural log of the absolute value of x, plus the numerator -1, or simply minus the natural log of the absolute value of x plus 1. And again, maybe you don't feel the substitution is necessary here because even though it has the exponent of 2 on it, the inside function is still linear with a coefficient of 1. It's just that here we would need the power rule rather than the natural logarithm. So this would be plus 9 times x plus 1 to the -1 over -1. And of course, as always, our plus c. Just to clean up that last term of this sum, we can write it as minus 9 over x plus 1. Now, in many cases here, the natural logarithms can be combined through properties of logarithms. That is not something that I am terribly concerned with. It is acceptable to me to leave it with the logarithms written separately. One more example will allow us to see how this works with a quadratic factor in the denominator. This time, our rational expression will be in the numerator 2x cubed minus 4x minus 8. In the denominator, we will have a pre-factored x times x minus 1 times x squared plus 4. Please note that if this had not already been in factored form, it would have been a degree 4 polynomial in the denominator, which would have been considerably more difficult to factor than a degree 3 or a degree 2 denominator. So the fact that it's already given to us factored is definitely a help. It saves us some trouble, which allows us to go straight to setting up the form of the partial fraction decomposition. There are 3 distinct factors. None of them are repeated, which is nice, but one of them is quadratic. So for our first factor, which is simply x, we will have a constant numerator. For our second factor, which is linear x minus 1, we will again have a constant numerator. But our third fraction has a quadratic denominator. Thus, its numerator will have to be linear. Again, the numerators of the partial fraction decomposition are always 1 degree less than the denominators. Now, it's possible that we might find that c is equal to 0, and if that's the case, then we would be left ultimately with a constant numerator, but we don't know that at this time. We need to account for the fact that there could, in theory, be an x term in that numerator. Once again, multiplying both sides by the least common denominator will give us 2x cubed minus 4x minus 8 on the left side. On the right side, we would have a times x minus 1 times x squared plus 4, because the x term would cancel out and would be the only factor that cancels out, plus b times x squared plus 4. In this case, it's the x minus 1 factor that cancels out, plus the entire numerator, cx plus d, be sure to keep that in parentheses, times the factor x times the factor x minus 1. In this case, it's the quadratic factor that cancels out. Admittedly, this is much larger than the previous two questions, but the same procedure can work here. We can eliminate some of the coefficients A, B, C, and D by carefully selecting the right values for x. Like before, since we have a single factor of x in some of these, selecting x equals 0 will make some of them just drop out entirely. To save us a little bit on the writing, I'm going to point out that if we let x equal 0 here, it will make both of these terms drop out completely. And therefore, just leave us with the left side when x is 0, and only the first term with the a when x is 0. So knowing that the choice of x equals 0 makes those other terms drop out saves us a bit of writing here. Cleaning this up, we are left with simply -8 on the left side. On the right side, we have a times -1 times 4, so that -8 is equal to -4a. And dividing both sides by -4, we find that a is equal to 2. In a similar fashion, if we allow x to equal 1, the x minus 1 factor in the first and third terms will make both of those drop out, thus leaving us with simply the middle one, and allow us therefore to solve for b. So again, with careful choices of x value, we can quickly and easily solve for at least some of these letters. On the left side, we will have 2 times 1 cubed minus 4 times 1 minus 8. And on the right side, with the first and third terms dropping out, we will have simply b times 1 times 1 squared plus 4. Simplifying the left side will give us -10. And on the right side, we will have 5 times b. Dividing both sides by 5 will give us -2 equals b. And we have our second coefficient, our second part of the numerator. Like in the previous example, we now do not have a way to get the a and b to both cancel out, because x squared plus 4 does not have any real number solutions. That's why it is part of why it is an irreducible quadratic factor. It does not have any real solutions here. So there's no value for x that we can choose that's going to make the first two terms of this drop out. But since we know the values of a and b, we can substitute them directly and use any other value of x we wish. However, since there are two unknowns that we're looking for, c and d, we're going to have to do this with two different x values. The simplest x values to choose we're going to have to use our known value for a and our known value for b. And we can pick any x values we want, but the easiest ones are probably -1. 1, whether it's positive or negative, tends to be very easy to evaluate things with. And since we've already used 0 and +1, possibly the next easiest number to use would simply be 2. It's the next smallest integer. It's positive. Could we pick any other number? Yes. Any other value for x would be acceptable, provided it's not one we've already used. So proceeding onward here, using x equals -1 along with a equals 2 and b equals -2, on the left side, 2 times -1 cubed minus 4 times -1 minus 8. On the right side, we're going to have 2 for a, -1 for x, minus 1, times -1 squared plus 4, plus -2 for b, times -1 for x, times -1 squared plus 4. And then we have cx plus d times x times x minus 1. Okay, so admittedly, this is big and ugly. But we can get there. The left side will simplify to -6 when we go through the arithmetic. The first term of the right side will turn into, well, the 2 is just 2, times -2 times 5, which gives us -20. The second term, -2 times -1 times 5, gives us +10. And the third term, -1 times -2 is +2, and that's going to have to distribute into the -c plus d. Giving us -2c plus 2d. Adding 20 and subtracting 10 from both sides will give us 4 is equal to -2c plus 2d, where we can divide everything by 2 and get 2 is equal to -c plus d. Now that doesn't seem overly helpful, but remember we have 2 unknown values that we want to solve for, which means we're going to need 2 equations. The only way to solve for 2 unknowns and get definitive values is to have 2 equations. This is where our other x value comes into play. X equals 2, along with our known values for a and b. A lot of stuff going on again, but again, if we're careful, we can work through it. The left side will actually simplify to 0. On the right side, the first term is 2 times 1 times 8, giving us 16. The second term is negative 2 times 2 times 8, giving us negative 32. And the third term is 2 times 1, or just 2, distributed into the 2c plus d, giving us 4c plus 2d. So again, rearranging all this, we're now going to end up with 16 is equal to 4c plus 2d. And what we now have are two equations that will allow us to solve for c and d. We could take a step further, as we did in the previous one, and divide both sides by 2, reducing this to 8 is equal to 2c plus d. Systems of equations can be solved in a few different ways. For a brief review of that here, in this case, since we're dealing with equations that are already set up in the same format, and because they were dealing with relatively small and integer coefficients, it's actually very easy to deal with this by multiplying both sides of the first equation by negative 1. We will be able to eliminate the d by turning the top equation into negative 2 is equal to positive c plus negative d, while the bottom equation stays 8 is equal to 2c plus d. By combining the two left sides of the equations with the two right sides, we find that the d cancels out, and we can divide both sides by 3, giving us c is equal to 2. From there, it's quite easy to find that d is equal to 4. And we now have the final two values for our fractions. Again, it's a lot of work. It takes up a lot of space. But this is the nature of the problems we're dealing with. We are now ready to rewrite our integral using our partial fraction decomposition. So our integral was originally 2x cubed minus 4x minus 8 over x times x minus 1 times x squared plus 4 dx. And this can now be rewritten as a over x, or 2 over x, plus b over x minus 1, where b is negative 2, plus cx plus d over x squared plus 4, where c is 2 and d is 4. Now, it is possible to work with that third fraction by leaving it as it is, but if we're observant, we can split that third fraction again into 2x over x squared plus 4 plus 4 over x squared plus 4. The third fraction, 2x over x squared plus 4, is going to lend itself very nicely to integration by substitution. Unlike the previous examples, this one we might actually choose to work with. So I'm going to pull that out. And we're going to let u equals x squared plus 4, so that du is equal to 2x dx. And we get a pretty clean substitution here. Which will simply result in the natural log of the absolute value of u, which is the natural log of the absolute value of x squared plus 4. Now, it is acceptable to leave that integral like that, but we may also recognize that x squared plus 4 is always going to be positive, and thus swap the absolute value for a basic set of parentheses. As for the 4 over x squared plus 4, we might recognize the denominator as a sum of squares, which, well, we could use trigonometric substitution on it, but we actually already have from Calculus 1, we actually already have an integration statement for this. It might help if we bring the numerator of 4 out in front and write this as 1 over x squared plus 4. This 1 over a sum of squares is actually in the format for the arctangent function. Using the integration identity for that, we have 1/2 times the arctangent of x over 2, where the 1/2 times the 4 combines to give us 2 times the arctangent of x over 2. Thus, our overall integral is going to be 2 times the natural log of the absolute value of x minus 2 times the natural log of the absolute value of x minus 1 plus the natural logarithm of x squared plus 4 plus 2 times the arctangent of x over 2, and of course, our plus c to round it out. A lot of work, a lot of steps, a lot of writing, a lot of places to make silly mistakes. Be careful in what you're doing here. Pay attention to all of your steps. And at the end, remember, if you choose to, you can always check your answer by differentiating it. It may take a little bit of algebra. Well, it took us 3 pages of this to fully complete this integration. So it will probably take a great deal of algebra to show that the derivative of this does become the form of the original integrand. But if you persist, you can get there.